All right, so it's a great pleasure to have John Chaika speak at the Infosys Chandrasekharan Colloquium this week. And he's going to tell us about translation surfaces and their connections. All yours, John.
Okay, so thank you very much to the organizers for giving me this opportunity to speak. So I plan to talk about translation surfaces, which are an object that I really like, and how they kind of naturally come up in some different problems. And I should say that I'm probably going to have a little bit of trouble monitoring the chat. So please feel free if you have any questions, just interrupting me and asking your questions. Okay, so the idea is I want to talk about how they're coming up, and this is going to include some joint work with Giovanni Forti and Alex Wright in separate projects. Okay, so the first place I'd like to talk about how translation surface comes up are billiards and polygons. So what I want to have is I have a shape that's a polygon. So you can see right here, I've got this triangle, and I've got a point here, and it's going to have a direction going this way. And the rules of the game are going to be you travel in a straight line. At constant speed. So we want to travel in a straight line at constant speed. So now we see that we're traveling in this direction, and we're going to keep going in that direction until something happens and we can't travel in a straight line anymore because we've run into one of the sides of our polygon. And when this happens, we're going to reflect our trajectories with the rule that the angle of incidence is equal to the angle of reflection. So what we have is we've got that these two angles are the same. So the angle of incidence when you hit a side reflect off. By the rules of elastic collision. Okay, so does this system make sense to everybody? Great. So let's talk a little bit about what this system is like. So this system, which I'll denote, so if Q is the polygon, the billiard flow is going to take place on its unit tangent bundle. So this is just Q across the circle, modded out by an equivalence relation. So this equivalence relation occurs at points on the boundary. And what it does is it identifies points where the angle of incidence is equal to the angle of reflection. So you want to identify those two angles. So if you make angle theta with the side that you're bouncing off of, then you'd identify that with pi minus theta. Those would be the two identified objects. Okay. Now, okay, so now X sub Q has a three-dimensional volume. Which comes just from the natural area, from the area on Q across the length on the circle, and this descends when you use the equivalence relation, okay? And just some general caveats are that points that orbit into vertices don't have a defined flow. Okay, so let's just kind of draw a little schematic. So let's say I'm going this direction. If I hit here, I don't know what I should do because it's at the meeting point of two different sides. So I don't know what the angle of it, I don't know which side I'm hitting. So the flow just isn't defined for those points, for the points that orbit into or from these vertices of the polygon. Is everybody okay with that? But this isn't too big of a deal. This is only a two-dimensional set. So the flow is still defined. Almost everywhere with respect to the volume. Is everyone okay with this? Great. So now there's a special situation. Which are so-called rational polygons. And that's when all the angles are rational multiples of pi. Okay. Now, in this situation, f to the t, let's say x sub q, is foliated. By f to the t invariant surfaces. Okay, so these are and we will see that these are translation surfaces. So briefly, why does this happen? This happens because if all of my angles are rational multiples of pi, then the group generated by reflections about lines parallel to the sides, about, say, the origin, is a finite group. And that's going to be all of the different angles that your billiard flow is going to be able to take. So your invariant surface in this three-dimensional tangent space, which is your polygon across all possible directions, will be the polygon cross the finite set of directions that your flow is able to take. Okay. Yeah. Any questions at this point?
So I'm looking at the chat and there's nothing. So it's going.
Okay, great.
Yeah.
Thanks. Okay, so let's get a little bit of a more kind of how we can see translation surfaces come up. And so the basic idea of this is that you want to reflect the table rather than the trajectory. Okay, so we have this trajectory that we were starting out with before, and in the past, and previously what we had done is we had reflected the trajectory off in that direction, right? But instead of that, what I want to do is I want to reflect the table. So what I've done is I've taken whatever table I started with, and my trajectory will keep going in a straight line, but the table has been reflected, okay? And if I want to figure out how that's connected to the trajectory in the original polygon, I would just take the reflection that sends this back to the original triangle, and I would take the trajectory along with it. Okay, so you can see what I do is I just reflect this back over to here, and I'd end up with a picture like I had here. Is everyone happy with that? Great, and of course, there's no real reason to stop at just one. You can kind of keep going, and then here we'd have another piece, and this would be reflected back like that, and it would keep going off of this side. Is everyone okay with that? Great. And so you repeat this procedure. And the flow is a straight line. And we want to identify copies with the same orientation. So what we're doing is we're keeping track of how our angle is changing by changing the copy of the polygon. And when we return to a copy of the polygon with the same orientation that we've seen before, that means that our flow is returning to a direction that we've seen before, and we just want to identify those. Is everyone okay with that?
Yes, yes.
Great. So, okay, so I think examples can be very helpful. So let's just do out an example of the billiard and the regular polygon. Now, unfortunately, the regular polygon has a lot of symmetries, so it's kind of hard to keep track of what the different directions are. So what I've done is I've added a little arrow here that tells you the direction you flow in. And so this copy, so let's look at another copy. So let's compare these two copies. So they look the same, but the flow that was in this direction will be in this direction on this copy. So they don't have the same orientation, even though they look like the same pentagon. Yeah, so this is the regular pentagon. Okay, and so I've drawn all of the possible different directions that you can take. So you notice there's 10 copies, and you can take 10 different directions for the flow. So if you start out flowing in a given direction, there'll only be 10 different directions that you'll be able to reach. And so and just to get a kind of a sense of what I mean by the identifications, if you look at this side here, it's going to actually be the same as this side over here, okay? So if I was going to reflect off of this side over here, I would end up with a new pentagon. I apologize, I'm not very good at drawing. So you'd end up with a new pentagon, but this would have the same orientation as this pentagon over here. So these are identified. And so the 10 copies I've had give me all possible copies. So if my billiard flow was flowing over to here, I could just identify it over to here. Is everyone happy about that?
Yeah, clear.
So let's kind of go through some of the features of what's going on here. So sides are identified in parallel. So sides are identified in pairs. And when the trajectory leaves the picture I've drawn, what you'll get is that you just kind of go to the identified side and you keep going. So then I think when I get here, I go out here and so forth. Okay. So that's the picture. And then a more complicated thing happens, which we also identify vertices. This gives identifications of vertices. So let's do a little bit of one example. So if I start out with this vertex here, that's going to be the same point as this vertex here. And that's because it's sort of the far left side of this side, which is the same as the other side, right? These two sides are the same. So this point here has to be the same as that point there. Okay? Now, similarly, this is also the bottom of this line here. And so it will be identified over to here. Okay? So maybe I can just kind of represent this as 1, 2, 3 following the identifications. And so as not to take too long, I'm just going to work my way through all of the other, just kind of tell you what the other identifications are for this particular vertex. So all of the points that I've drawn on red, they're the same point. So okay. All right, and so on this picture with our identifications, the billiard flow is just a straight line flow. So on our picture, so here, our billiard flow is just the straight line flow. Okay, and just to kind of capture what's going on. So once again, we're in the unitangent bundle to our space. We have, our space is this regular pentagon across all of the possible directions in the circle. But from a fixed direction, we can only see 10 other directions. And this is keeping track of all of the 10 other directions that we can see. And so what we have is in this three-dimensional space, we have an invariant surface, which is 2 dimensions, where our flow in a given direction will be stuck in. So is everyone happy with this connection, how we've moved from sort of the direction changing in our polygon to changing the shape of our polygon and keeping on flowing in a straight line?
Yes, yes, perfectly.
Great. And then I just want to, as an aside, mention how this is a translation surface. So what do we have? We have a surface with a structure on it. And that structure is given by, so you can think of this picture I've drawn as being a chart. So this is a surface with a chart, with charts, where transition functions between charts are translations. And what I've drawn for you is the actual chart, right? This is just the chart itself. And when you go off the side, you get translated over here. So this whole picture is a chart. But I'm doing a slight lie to you. This is only true away from the vertices. And these are going to be cone point singularities. Cone point singularities. With angle and 2 pi, which are natural number multiples of 2 pi. Okay, so now maybe I can just make a few remarks. So you could do an Euler characteristic computation here. And there are, I think, 5 vertices. The vertices are identified in 5 classes. And so an Euler characteristic computation tells you that this is a genus 6 surface. And so this is a special structure on a genus 6 Riemann surface. So it's a genus 6 Riemann surface, that's some particular surface, with an additional structure given to you by these charts. And it's possible for a given genus 6 Riemann surface to have multiple such structures on it. Okay. Are there any questions at this point? Because now I'm going to talk about results. Great. Okay, so the starting point for what I want to talk about is Kirchhoff, Maser, and Smiley. And what did they do? They showed two results that are connected. So for rational polygons, they showed that the billiard flow is basically as ergodic as it can be. Yes, pretty much. So this is a bunch of caveats. So I'll be a little bit more explicit in a second. Okay. So what's going on with this thing? The flow in the rational case is stuck in invariant surfaces. So what they prove is that the flow is ergodic with respect to area on these FT invariant surfaces. The flow restricted to almost every FT invariant surface. Is ergodic with respect to the area. Okay, so this is an invariant surface, and so it has a natural area on it, right? We have this invariant surface in our unit tangent bundle that I've drawn a picture of here, and it has an well-defined area on it, right? It's just the area on the polygon, but you get 10 different copies of that, and you're ergodic with respect to that. So this is as ergodic as you can be, modulo the minor caveat that we don't get this for every FT invariant surface, but just almost every one of them, where that almost every is with respect to the natural length on the circle, which is keeping track of your directions. Okay, so does that result make sense to everybody? Great. And so they then use this result to say, oh, yes?
Yeah, quick question. So what are the exceptional surfaces here?
Okay, so this is kind of an interesting thing. So exceptional things can come in a variety of different ways. So one way you could be exceptional is you could actually have that your trajectories are sort of periodic in these invariant surfaces, or you have a positive measure set of periodic trajectories in the invariant surfaces. And in the case where you come from a regular polygon, Veach proved that the only things that can happen is that you're either ergodic on your invariant surface, and even more, you're uniquely ergodic, or you are completely periodic in your invariant surface. But this is not true for all billiards. So there are billiards where you can sort of split into different minimal components, or you could split into minimal component and a periodic component, and even something weirder can happen, where you can have that you're ergodic, but not where you're not ergodic with respect to sort of the natural area class. And what really happens is that every orbit is dense for particular directions. Every orbit is dense in its invariant surface, but they equidistribute for different measures. And so you can actually build examples of this in rectangles with additional barriers. So you have a rectangle and you carefully choose an additional barrier, and you can build special directions that have this property. Did I answer your question, Mahan?
Yeah, thanks. Did you hint at ergodic but not uniquely ergodic in these exceptional examples, or was that a misunderstanding of what you said?
Yeah, no, that's a great point, Mahan. So these examples they are going to be, so what Kirchhoff, Maser, and Smiley did is they showed that the flow on almost every invariant surface is actually uniquely ergodic. What that means is the orbit of every point equidistributes for one and the same measure, which is the area on that invariant surface. But there are special billiards in sort of L-shaped tables where you can make area to be ergodic, but not uniquely ergodic. So sort of you can have a range of different behaviors. Thank you for these questions. Did I answer that?
Yeah, absolutely, absolutely. Thanks, sir. Thanks.
Cool. Does anybody have any other questions? In particular, does everybody know what the word ergodic means?
Yes, I think that's ergodic.
Great. Okay, as a result of this, they showed that there is a billiard and a polygon. Which is ergodic with respect to volume. Okay, and let me just say that this can't be rational. Because you can't have your flow stay trapped in invariant surfaces. Okay, so by proving a result about rational polygons and really about all translation surfaces, they're able to derive a result that cannot possibly be true for rational polygons. And I hope to explain a little bit how this deduction of 2 from 1 goes. And I sort of won't have, explaining how 1 comes is sort of beyond the scope of this talk. Okay. Forney and I have recently improved this result. And we kind of have a similar sort of 2-part setup. So for rational polygons, the billiard flow, the product of the billiard flow in different directions is almost surely ergodic. In almost every pair of invariant surfaces. With respect to the product of area in itself. Okay, let me try and explain a little bit about what I mean by that. So if I start flowing in 2 different directions on this surface, so maybe I start flowing in this direction and in this direction, I can make a couple of boxes, maybe a blue blah box here, and maybe I'll make another blue box here. And I can ask, how much time does the trajectory in this direction land in this box while the trajectory in this direction lands in this box at the same time? And so what we prove is that for almost every pair of directions, it's going to be proportional to the area squared of these boxes, right? The proportion of the product of these 2 boxes to the product of the 2 invariant surfaces. Did that make sense?
Yeah, so John, can one reword this in terms of, say, an R2 acting on the, I mean, it's a geodesic flow, cross-geodesic flow? Is that?
No.
And the
so
result,
we're looking at the diagonal action on the 2, right? So you're flowing at the same speed in 2 different directions, and you're not letting yourself sort of move the different directions independently. If we were doing this would follow from Maser's, Kirchhoff, Maser, Smiley. Thanks for that question, Mahad.
Okay, thank you.
And as a result of this, we prove that there exists a billiard and a polygon which is weak mixing. And I'll define weak mixing in a moment. And once again, this can't be rational. Is everyone happy about this?
Yes.
Great. So do people know what weak mixing means? All right.
It might be a good idea to remind. Yeah.
Okay.
Yeah.
So there's various ways, especially if you're not familiar with the definition, to try and convince people it's important.
Can I? Sorry for interrupting. Yeah, I have a question. Quick question. So, going back to the previous setup where you have a polygon with rational angles. So, are all FT invariant subspaces going to be of the same topological type as the one we constructed by identifying the reflected polygons?
I think that the answer might be sort of no for sort of, I'm not positive. And I think it might mean a little bit what you mean. So I think one thing I'd worry about is that you sort of have a big FT invariant subsurface, but it has some FT invariant subsurfaces of itself, which sort of have different topology.
All right. So we should be talking about ones which are irreducible in some sense.
Yeah, probably.
Okay.
Okay. Yeah. Any other questions? Great, thank you for that, Ritwik. I hope I didn't mangle your name too badly. Okay, so there's different ways to sort of convince somebody that a definition that they're not familiar with is important. And I'm going to take the tack of giving you a lot of equivalent conditions. And my argument is going to be that this definition is probably a little bit important because it shows up in many different guises. Okay? So your probability measure preserving system is weakly mixing if any of the following equivalent conditions happen. So all of these conditions are equivalent and they're all can be used as a definition for weak mixing. So the first thing is that your product flow with yourself is ergodic with respect to your product measure. And so maybe tying this back to Mahan's question, what I'm not doing is I'm not saying f of t, f of s here. I'm making you flow at the same speed in both coordinates. Okay? Great. The next thing is that the product of any, that your product is actually ergodic with respect to any other flow. So sort of the flow that you're least likely to be ergodic with respect to is yourself. And so if you're ergodic with respect to the product with yourself, you're actually ergodic with respect to the flow, with respect to any other ergodic flow. Okay? There's also a spectral categorization, which is that you have no non-trivial eigenfunctions in L2 of your area. So all of these flows have a trivial eigenfunction given by the constant functions. Its eigenvalue is 0. So if you flow for time t, the amount you change the value of your eigenfunction is by e to the 2 pi I times 0, times t times 0. Okay, so that's a spectral categorization. Another thing is if you fix so what we're doing initially is we're doing a flow. So you have an R action and you can flow for sort of any amount of time, but maybe I just want to stop along the integers. So I flow for time 1 and I look at what happened. And I flow for time 2 and I look at what happened. Then I flow for time exactly 3 and I look at what happened. And I stop at these discrete moments in time along this arithmetic progression. And that's going to be ergodic as a Z system with respect to mu for all R, except for the one where it's obviously not true for, which is when it's 0. If you flow for time 0, then you're just the identity map and you're not going to be ergodic. Now, none of these definitions seem at all to be involved with mixing. But that comes into the fact in definition 5, which is that there exists a sequence where if you flow forward a set along that sequence, it becomes asymptotically independent from any other fixed set, okay? So as I move my set A forward and I look at its intersection with B, that converges to what you would have happen if everything was independent, which is just it's the product of the measures. And we call this sequence a mixing sequence. And your transformation is mixing if any sequence going to infinity is a mixing sequence, okay? Now, these mixing sequences are not rare. If you have one of them, then really most sequences that you choose going off to infinity will be. And in particular, there's a density 1 subset of the reals, so that any sequence in it going to infinity is a mixing sequence for this transformation. Does everybody understand what I mean by a density 1 set of the reals?
Yes.
Great, cool. Are there any questions on weak mixing? Great. Okay, so maybe unsurprisingly, the way in which we show that our flow, that our billiard flow is weak mixing with respect to volume is by condition 1. We show that its product with itself is going to be ergodic. Okay, and then we get for free all of these other equivalences. Okay, so I want to talk a little bit about how results 2 follow from 1. And I'm going to do this in the case of Kirchhoff-Maser-Smiley, where everything is sort of a little simpler. The case of my work with Giovanni, it's similar, but you just replace every time you see the unit tangent bundle, x sub q, you replace it with, and anytime you see the unit tangent bundle, you replace it with the product of the unit tangent bundle with itself. Okay, so I want to give you guys a sketch of why this is true. So the first fact is ergodic is a sort of not an open or a closed condition. It's kind of a G delta condition, but approximately ergodic, whatever that means, is an open condition. Okay. Now the second is, so I've left some space, so I'm going to go back to these points, but I first want to I first want to just sort of outline how the argument's going to go, and then I'll go back and give a little bit more detail on these points. Now the second thing is that if x sub q is rational, if q is rational, but not too rational, with complicated sides, by Kirchhoff-Maser-Smiley, the billiard flow is approximately ergodic. Okay, so now as a result of this, what we get is that approximate ergodic is an open and dense set. And then what we do is we invoke the bare category theorem. Which will say that the intersection of better and better approximately ergodic is non-empty. And this points in this intersection are actually ergodic.
So I have a
Yes.
question.
Yes.
So billiard we are considering is the convex billiard.
Oh, this is about all billiards and polygons. They don't need to be convex. So in particular, in this picture I started with, yeah, let's go back to a picture I started with. I could have removed from it like a little box here. And so we could consider the billiard flow happening in this shape. So I'd reflect off when I went into that, reflected off of the sides. This also shows up in my answer to Mahan, because if you consider in a billiard in a rectangle that has an additional horizontal barrier, that's not going to really be a convex polygon. Did I answer your question, Ji-young?
Yeah, then the rectangle is also must have the rational angles.
Yeah, so this would ask that all of the angles are rational multiples of Q. So this box I drew, if you compare the angle that one of its sides makes with one of the angles on the outside, the difference of those is a rational multiple of pi.
Okay, thank you.
Thank you for the question, Gian. Any other questions? Great. So I want to define what approximately ergodic is. So let's give a sort of idiosyncratic definition of ergodic, which will motivate our definition of approximate ergodic. So what we want to do is I want to look at the time averages. So I look at from 0 to t, 1 over t, and I want to look at g of f to the t of x. Okay, and I want to subtract that from the integral over g over my entire unit tangent bundle with respect to the volume. Okay, so ergodic means that almost everywhere this goes to 0. Okay, so as a consequence of that, what you're also going to have is you're going to say that if I integrate this over x sub q, and I do this d volume, okay, this goes to 0. And let's say for all at 1 Lipschitz f, sorry, 1 Lipschitz g. Okay, so I can define sort of the path metric on my unit tangent bundle to my billiard table, this x sub q space, and I can probe the space of functions on that by looking at the 1 Lipschitz condition. In your ergodic, if and only if this is true for all 1 Lipschitz functions. Is everyone happy about that? Okay, now what I want to do, so that's ergodic on the nose. And what I want to do is I want to come up with the notion of approximate ergodic. So what I want to say is that there exists a t so that this integral okay. That this is less than epsilon. So there exists a t so that this is less than epsilon. Now now if I fixed g, this would be an open condition depending on epsilon. But if I let myself have all g, this condition being chosen is contained in the interior where this is less than 2 epsilon for all 1 Lipschitz functions. So it's basically an open condition. In the sense that its interior is non-empty and emits approximation of a slightly, contains an open neighborhood of those that emit a slightly better approximation. any questions on this notion of approximate ergodicity? Great. So now if my polygon is rational, but with a complicated angle, then if I look at reflections about two of the sides, and I look at the composition of those, that could contain a very small rotation by a very small angle. And what this is going to mean is it's going to mean that my invariant surface is pretty dense in the unit tangent bundle. And even more, it's sort of probing the different directions very close to the way the volume on the unit tangent bundle would approximate it. So if I have a complicated thing, then in the presence of Kirchhoff, Maser, and Smiley, I'm approximately ergodic for some epsilon. So just a word on the quantifiers. So if I fix my epsilon greater than 0, there's a complicatedness enough of the, rational relationships so that any billiards that are at least that complicated will have that their billiard flow is approximately ergodic for this fixed epsilon that we fixed ahead of. And that's an immediate consequence of Kirchhoff, Maser, and Smiley. Okay. And so now the next fact is that approximately ergodic of class epsilon, of amount epsilon, is an open and dense set. And so the Bayer category theorem tells me that if I pick a sequence of epsilon i's going to 0, and it's countable, the intersection of these open and dense sets is non-empty of this countable number. But those are going to be approximately ergodic for all epsilon greater than 0. And that implies, just from the setup, that you're going to actually be ergodic on the nose. Okay? And so that's how Kirchhoff, Maser, and Smiley's work happens. Okay. Are there any questions on this? So the deduction of 2 from 1 for my work with Forney is very similar, but you just consider the product of the unit tangent bundle with itself. Okay, and that's how the argument will go. All right, so I don't think I have time to get to the other results I was planning on talking about or the other connections, so I'm sorry about that, but yeah. I guess I should probably stop now because it's 8:50.
John?
Yes.
You still have some 10 minutes if you'd like to tell us a little bit about the other results. That'd be great.
Okay, maybe I'll just kind of quickly tell you about one of the other results. So I want to give you a translation surface that doesn't come from a billiard in a polygon here. So once again, what is this going to be? It's going to be a surface. In this case, this is a genus 2 surface. And the sides come in pairs, which I've colored appropriately. So this red side is paired with this red side, this yellow side is paired with this yellow side, this purple side is paired with this purple side. And so once again, these sides come in pairs, and this is another picture of a translation surface that probably doesn't come from a billiard. And let me just say a few words. Once again, you run into problems at the vertices. In this case, the vertices are going to be identified in 2 classes, each of which will have cone angle 4 pi. Okay, and like in the case of the billiard, we have a flow in every direction on this translation surface. And that's just because translations preserve directions. Okay. So we have this nice kind of object. And so I want to talk about smooth flows on surfaces. So this translation flow is not smooth. It's not even defined everywhere. And the problem is, once again, you don't know what to do with points that go into the vertices. Okay, but there's a fix to this. What you could do is you could make the flow be fixed at all of the vertices. So the flow doesn't move at all when I start out the vertices. Okay, that still is sort of a weird object, because when you're flowing into the vertex, you end up at the vertex in finite time. Also, when you flow on one side or on the other, you're still going to be far from being smooth there. But you can fix this by slowing down the flow near the vertices. So to make it smooth, make vertices fixed point and slow the flow near vertices. Okay, so maybe I can just sort of draw a schematic example of what this would be. So here's a translation surface. I identify these two slits. So if I come in here, I come out there. And here are going to be my two vertices. They come in two classes, each of cone angle 4 pi. And so if I look at what the flow looks like when I'm returning to these two sides here, what it's going to look like is I'm going to, well, start here, and then it takes me a longer time as I get close to these vertices. To the vertices themselves, it'll take infinite time. Okay. And then I have a similar picture on the other side. Okay, and this is so what the return function, what the return time function of the flow to these two sides look like. Okay, so this is the return time function to the two sides. Okay. So, and if you notice, this saves us from the issue, this has a chance of saving us from the issues of the lack of smoothness, because if I'm traveling on this side of the thing, of the cone point, as opposed to this side, one of them is going to come out here, the other is going to just sort of keep moving, right? But they're going extremely slowly. So this sort of drastic change in placement happens extremely slowly, and so the flow can still be smooth if we slow down near the vertices appropriately. Did that make sense?
Yes, yes.
Great. So this has been used to study smooth flows on surfaces. And so let me just mention some results. So the results are Katok found the maximal number. Oh, let me just be very clear. This is a flow on a surface, not a unit tangent bundle to a surface. The maximal number of invariant, fully supported ergodic probability measures of invariant, fully supported probability measures. And this is when all singularities are non-degenerate, when fixed points of flow are non-degenerate. And this number is a very natural number, it's just the genus of the surface. Kachirgin found mixing examples, showed mixing was typical. when singularities are non-degenerate. When fixed points are non-degenerate. I'm sorry, fixed points are degenerate. And Alex Wright and I constructed an example with all fixed points degenerate, non-degenerate. And by a result of Ulchegrai, these are atypical. An earlier result of Ulchegrai. So she didn't have any examples to show it could occur or not, but she just showed that usually it doesn't occur. Okay, I think I should probably stop here.
All right, so let's thank John for the lovely talk.
Great talk, John. Thank you.
Excellent, thank you. Are there any questions? All right, I guess all the questions were during the talk. So thank you, John. Really lovely.
Yeah,
Oh, Manav.
Anish, yeah. No, I mean, I'm in two minds about whether to ask this or not.
No,
Because
go ahead, please.
essentially, can you expand on typical and atypical?
Yeah, so this construction, what it's giving you is it's giving you a, so it turns out that it's sort of kind of clear how you want to slow down near the singularities. So in the case where your singularities are cone angle of say 4 pi, you want to slow down like distance to the singularity. That's what's smooth, because you near your cone point, the chart looks like z goes to z squared. So this is actually a smooth operation near these cone points.
Yeah.
Okay. So then you could just kind of pick a typical translation surface, and you could just sort of talk about that. And that's what typical means in this setting.
I see.
It's sort of a natural way to prove it when you don't have saddle loops, when you don't have periodic.
I see. Okay.
Regions.
Okay. Thank you.
Thanks for that.
Yeah, I don't have a question, but are there any references for the last 3 results and the other 2 results that you mentioned in the?
Yeah, so this will take me a moment to, so if you look at my paper with Alex Wright, we have a lot of references there.
Okay.
And so this result of Katox is from the 70s. And I think that was sort of around when Kuchergin was doing his result. And Karina's result is, I guess, from around 2010, maybe 2008. It's an annals paper, so.
Okay, thanks.
Yeah, and this is my only paper with Alex Wright. So you can Google Alex Wright Chaika archive, and it should be the first hit.
Only paper yet, so far. Okay. Anything else? Any other questions or comments? If not, let's thank John again for a really lovely talk. Thanks, John.
And thank you guys for attending with great questions.
Oh, no, it was great. Yeah. So once the pandemic is over, do come down and visit us.
John, I think Mark just sends a message on what. I mean, Anish, would you like to read that out?
Yeah. So Mark Polycott says that he enjoyed the talk and has a smiley face on.
Thanks, Mark.
All right, great. Okay, thanks again, John.